So thank you, everybody. So thank you, everyone, for joining us today once again. We're really grateful for your support over the years. My name is Bilikisu. I'm the founder and co-organizer of the Abuja R User Group. And today we're going to be looking at algorithmic elegance, fractal symphony in R. So our speaker today is Abhirup, Moitra. Hope I got that right now. Okay, so
Yes,
Abhi
now
is
you are
an
better from the previous.
oh, thank you. So Abhi is an independent thinker, curious learner, and explorer of the universe. Since childhood, he has been trying to understand how the whole universe works. Okay, so and how is arranged together. Was with this the clockwork behind it that makes it run the way it is? Currently, he is pursuing his master's in mathematics with dairy science from the Institute of Mathematics and Application. Um, Bhu-
Yes, simply call India.
Bhubaneswar. Okay, in India. Okay, okay, don't worry. Um, so Abby aspires to cultivate expertise in machine learning and deep learning, approaching them from both theoretical and computing angles. Moreover, his goals is one of his goals, that's it, is to apply this knowledge to the study of data-driven dynamical systems, chaos, fractals, and astrostatistics. So Abby is a course instructor at an educational company named Cosmic Carriage, where he co-instruct the course, and the course are programming for everyone. Okay. He is known for his impeccable blog writing skills, which enable him to effectively communicate complex ideas in an engaging manner. So please join me in welcoming Abby. Today, again, he's been an active supporter of our group, Abuja R User Group. He's been a friend, he's been a close one, though far away, but he's close to our hearts. Is somebody that I really appreciate. And thank you so much once again for joining us, Abby.
Uh, Thank you again, Billy Kisu, from
Thank you.
your uh, the lovely introductions and such a warm welcome. And I will say that you have improved your pronunciation to call my name. Okay.
Yay! Don't worry. I'll get better. I'll
So,
get better with that.
yeah, actually, I believe that now, actually, we're in virtual meets and stuff. But I hope Abuja our user group and me, I'm a like a family we are, okay, and working under
Yeah.
one roof. So
Yes, yes.
so the first experience was lovely, and this is the second time I am presenting my small work. I mean, a very uh, so these things are very complicated, you know. I mean, when I started to work when I was in BSc, in my bachelor in the year 2021. But actually, the motivation comes at very beginning, when I don't know why I just started to work these things, just to curiosity, or as I love to uh, explore the things surrounding uh, me. And these things are very complicated, as I'm throughout the war, the whole talks I will say, because actually there are so many mathematics, very robust mathematics working behind it, uh, and doing this sort of things in a very small laptop or any personal PC is very difficult, until or unless the institute or any other you will get particular research laboratory where you will get to scope to perform parallel computings, so many what should I say, uh, I mean the computational. So here actually the challenge is from the computational perspective, I would say. Okay, maybe there you will get the mathematics, maybe uh, what should I say, very complicated, but when you write the code and try to when you clear the mathematical things and try to engage yourself to building up your algorithms, but the challenge is to test your algorithms. Okay, so until or unless if you don't uh, test your algorithms, okay, if you don't so you will not get the answer that whether you are correct or not. So I'll say that think of nature as a giant puzzle where everything fits together perfectly. So how tree branches split into smaller branches, so which split into even smaller ones. So that's like a math thing called a fractal. Okay, where patterns repeat themselves at different levels. So when you look at a tree or shell or even a mountain range, okay, so or even a mountain, I will say, so you see these repeating shapes and patterns, isn't it? So it's kind of like zooming in on a picture and seeing the same thing over and over again. So just smaller each time. So nature follows a simple rules to create all this complexity, just like how a fractal is made from a simple math formula. That is the main discussion today. Uh, that is the unveiling the nature's code, right? So so at the first we look pretty random things, um, but sooner familiar from emerges. So you see the trajectories, okay, the trajectories that begin on the edges seem to speed of random directions. Okay, so but all those that begin within a certain uh, space end up in the attractor. Now, if you ask me that what does this attractor mean to us? So attractor is nothing but the set of points in our phase space. Now phase space is like so if you, I'm not going any very hardcore mathematics things. So these are 8th standard or you can say 9th standard knowledge. So so if you just imagine a Cartesian coordinates, and in the base one is the x coordinate and uh, uh, the horizontal thing is the y coordinates. So each point in that space is a unique state of the system. So for a specific system, so if you say suppose imagine that you are trying to scatter a bunch of random points around to uh, represent the different possible states. So how it look like? So this is your Cartesian coordinate. So actually somehow I am unable to join from my tablet, so that I can pen tablet, so that I can show you the things what I want to mean. Okay, no issues, but if you try to concentrate here. So actually I'm not going very deep into any theoretical things, no worry about that. So if you just I mean, I'm just casually gossiping with you, okay? So as I was saying, as I am saying that So that Cartesian coordinate, you just think about that. So the vector fields look like there. So try to scatter a bunch of random points there, so around to represent the different possible states, and you'll see how they evolve and move around. It seems like the spiral towards the center, isn't it? So that is the thing, or that is the idea comes around, and like the attractor. So from there, the attractor is a set of points in the phase space which attracts all the trajectories in a certain area surrounding there. Okay, so I'm not going very mathematical things, and this is not our discussions cause of I mean concern about a discussion. So it might seem like their starting positions no longer matter if you just see here in this animated part. Okay, so but once they reach the attractor, their trajectories diverge, so each following its path indefinitely, and they never cross. So the small differences in their start positions lead to the increasingly different futures. I mean, the different, I mean, uh, future outcomes or different decisions. Okay. So this is the posterior child theory, child of chaos theory, and uh, this is the sometimes almost synonymous with the butterfly effect. Okay, or the field of chaos theory itself. So it even looks like a butterfly. So now there is a thing I have pointed out here. These things, you can write these things out. So trajectories are just curves, so they should be one dimensional, right? But how come no matter how much you zoom, okay, so I am unable to share my animated things. So okay, let it be. So animated part, I'm not animated, like 3D I have prepared. So in our past discussion session, I just presented that thing. So if you just zoom in on this attractor, you can always find more and more trajectories everywhere, isn't it? So this is the reason that this attractor is said to have a non-integer dimension. So it's made up of infinitely long curves in a finite space, so which are so detailed that they start to partially fill up a higher dimension. So it's not one dimensional. Okay, so if you are thinking that it is one dimensional or two dimensional, so this is not even three dimensional. So it's dimension in somewhere in between. Okay, so as a result of its non-integer dimension and detailed uh, arbitrarily small scales of uh, uh, sorry. So Biliki, so can you tell me that how to hide this screen? I mean, hide this bar here.
Okay.
Yeah,
Which
yeah,
of the
can you
bar, the Zumba?
where?
Okay,
Yes,
your
yes. How to hide
presentation.
this zoom bar actually? Yeah.
I actually I don't know.
So
Okay. Let me just pause it, then we'll try to get
okay.
Zoom.
Okay. Sure. So yeah, as I'm saying that it's dimensioning somewhere in between 1, 2, or 3. So as a result of this non-integer dimension and detail of arbitrarily small scales, the set of points in this attractor is a fractal space, and that's why it's a strange attractor. Okay, so the dimension, okay, is not something one or two. So here comes the idea of fractal space. So So this is you maybe seen before, I mean before my talks and anywhere. So this is called the strange attractor because of its strange behavior and the strange shape and strange facts associated with this idea. So that's why I'll say that this I mean this dimension is in fractal space, and fractal space uh, dimension is uh, non-integer, that is the fractional dimension. So from the fractional, the word fractional mean to the fractal, that is, that's how the idea actually come out. So chaos present in everything from a drop of water to the galaxies in our universe has long fascinated people from cultures around the world. The natural disorder present in the branches of trees, lightning and coastlines, to name a few examples, may seem to be completely chaotic. However, the self-similarities within this phenomena is much more organized than it appears. So, repeating patterns in many natural objects and process are known as fractal figure, that is shown here. So here it is the image of a coastal side of a country. Okay, and this is also what should I say? This is snowflake. Okay, so everything there will be a I mean nature. You'll see these are the self similar patterns. Okay, so why I am saying the self similar, not exactly same. Self similarity means, I'm very in a layman terminology, if I say that uh, say suppose this is my finger. Okay, so this is my finger, and see these things. So these are my some patterns. If you look in your hand, the palm or the finger, so these are maybe similarities are there, but they are identical. That's why if you press I mean the fingerprint lock. Okay, so you are pressing with that point in your using your thumb, right hand thumb. Okay, so only it will only uh, open, unlock your system, unlock your phone system using this thumbs fingerprints, not this one, because they are identical. Okay, so that's why wherever you see observe the pattern in nature, uh, that is identical in nature, and there is self similarity you will find. Okay, so self similarity within this phenomena is much more organized than it appears. So repeating patterns in many natural objects and process are known as fractal figures. That's how we see. Okay, so now I'll say that fractals are patterns from what is known as a chaotic equations. So chaotic equations you can found anywhere if you just Google these things. Any chaotic equations, chaotic systems, how these things. I mean, also if you just figure out the go and search the strange attractors equations, chaotic equations, any just equation, so they exhibit uh I mean so they exhibit self similar patterns of complexities regardless the magnification. So when divided into parts, they produce a nearly identical uh, reduced size copy of the whole. So with fractals, uh, infinitely complexity is formed with relatively simple equations as well. So by iterating or repeating these equations many times, like random outputs create amazing pattern. So that are the unique yet recognizable. So however, most fractal is in nature do not repeat forever. Definitely you should keep it in mind. So the repetition eventually breaks down in natural patterns. So and the so in many cases, okay, fractal patterns are most efficient way to deliver nutrient harvested sunlight or from support structures for the plants of or animals. Okay, so now we are entering the realm of fractals. Actually, you see, the geometry or the ancient mathematical disciplines has been studied for centuries by notable thinkers such as Plato, Euclid, and Pythagoras. So, however, the advent of modern computing technology has uh, paved the way for a revolutionary approach to geometry. So one individual at the forefront of this, I mean, uh, this realm, or what is the right word to say? The paradigm. This paradigm. So this shift is sorry, mispronunciation. Benoit Mandelbrot. So this is the French pronunciation. I could be wrong. So it's a Benoit Mandelbrot. So he has a visionary. So he was a IBM fellow. So embarked on a quest that how that uh, would forever change the landscape of geometry. So Mandelbrot's journey began with a simple yet profound questions that how long is the coast of Britannia? Okay, seems simple, right? But there is a twist. There is a twist, I would say. So, so Mandelbrot's answer was unexpected. So it depends on who's measuring. Okay. So yeah, something. Someone is trying to say anything. I hope no. Okay. All right. So
If you, sorry, if you have any question, just kind of signify that you want to ask question or pass them to the chat.
yeah, any
Thank you.
question is popped up. I hope there is no such questions. Would you share the slides? Yeah, definitely. Actually, it is available in my website. So after this end of this session, end of this webinar, I will mention everything from where the things you can read these things out. Actually, uh, after these talks, I will definitely actually I have already ready with some proper documentations of this fractal things. Also, I'm preparing some of the uh, documentations. I am in between some of the work. So yeah, all these things, whatever I used to do, that is available in my website, and everything is open source. Okay, so no worry, I will definitely share. Even if you want to discuss something, there will be a constructive discussion. No issues. Okay, I am, feel free to reach out, and I'm always there to learn basically. So it could be any algorithmic things, or it could be anything coding things as well. Even also the mathematical things. Actually, I don't have any such mentor of this line. Okay, so I'm looking for a mentor. So, so I, so only mentor is a book. So, so I'm reading books, articles. I mean, uh, just playing with my algorithmic skills, having fun with that. That's all. So yeah, coming back to our discussion, that is, so as I'm saying that how Mandelbrot started his idea. So So he said that if you are a person walking along the coast, so this is the coastal side, or the image or the map of a coastal side taken from a satellite. So first at all, I will say you parallelly watch both of the uh, image. Yeah, there is a question, why need to concept of why we need the concept of fractals? What is the application of the fractal theory? Yeah, definitely I will definitely discuss all these things out. Okay, so no worry, there is a boy, Indrajit Kundu. Yeah, this is a lovely one. uh, Thank you for asking such questions. So uh, see, there are many reasons to work with fractal things. Actually, in nature, we'll always uh, see fractal, like why do we need? That is the first question. So, in a very uh, have you ever see any image of heart? So, or the bone structure. Okay, so study that things out. Uh, that is the analogy behind this is nothing but fractal things. Okay, the whole study is surrounding with fractals. Even in a graphics designing, so in a game designing, the visual graphics things. There are also some, you'll see the fractal image study. Okay, so even universe, spiral galaxies, and any uh, uh, I will say the galaxy is also surrounded with the fractal stuffs. So fractals, I mean, uh, is a study where the computing, computer science, computing the stuffs, and the pure mathematics things embracing each other. Okay, so even you see uh, 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 yeah, antenna, any antenna, or any study of any geometrical figures. Okay, so there also you'll find the fractal thing. So it is not something like you just study the things, the formula you just study out and you will learn fractals. No, you have to keep observe yourself, you have to prepare yourself in that way. But a very detailed discussions and stuff will definitely come. So yeah, so coming back to our topic again. So yeah, so Mendelbro stated that if you are a person walking along the coast, so how many kilometers is it? So hard to say, definitely. But if you are a rabbit following the coastline, so it's longer. Now picture yourself as an ant. Okay, so it's a whole different story. The coastline seems endless. So this idea intrigued by Mendelbro. So also when ants look at a coast, so it's like an astronaut. Like yeah, I mean compare yourself as a. I mean think like you are viewing these things from a space. Okay, so you are observing these whole things from a space, and you are an astronaut. So it's like an astronaut viewing it from space. So both seem the same thing, just at different size. So this is called the self similarity. Okay, and our next discussion start from the idea of self-similarity and fractal. So self-similarity is a fascinating property observed in nature. So from yeah, Bilikisu, yes. Yes, you have
Okay,
a question.
there's a question
Oh,
in
there
the
is a
chat.
question in chat box. Okay.
Yeah.
He's asking that is it basically we observe patterns of similar events and see their distribution and apply mathematics to get that fractional design? Yeah, definitely. Actually, when you'll start with some of these ideas, not all cases, because when you'll study the fractal patterns in Farn. Okay, so there is a famous name called Barnsley Fern. Okay, so Barnsley Fern, actually Michael Barnsley. So Michael Barnsley actually studied these sort of things, and actually think the one of the best methodology is I believe that is the iterated function system. Now, don't say what is iterated function system things, because these things started from the discussions with mathematical analysis things, the matrix space. There is a lots of idea mathematics things, the fixed point iteration things. So iterative methods or the fixed point iteration method, one of the best methodology to uh, generate the fractal pattern. So we observe patterns of similar events. So he's saying is see their distribution and things are definitely in many cases we how can I generate fractal abstractly? Well, abstractly, can you elaborate the word abstractly?
Yeah,
Yeah, definitely.
yeah,
You can ask. Feel free to ask.
yeah, yeah. We can getting the common technique. What it it is function system or L system, which is numerical method. Yes or no?
Definitely.
Yeah. I say which is the abstract, which is not numerical, like which is any which we we can get the exact the value of or exact the system which I can see the
Yes.
abstractly.
Yes. So, see, actually, I'm not reached that part. The Barnsley font things, which I want to introduce here. But still, uh, yeah, definitely. I am elaborating things in a very, in a very short way. I shouldn't, because if I go to elaborate all these things out, it will take. Uh, I mean, these are the I will say the session of 10, 20 sessions I should take in such things. But here I'm also engaged of doing these things. I'm exploring and studying these things very from the very mathematical and computational perspective. Even I'll not claim that I know everything of it, but the thing is, the boy Indrajit is saying is that so the Barnsley fern is one of the best example. Okay. Um, or so the abstract way is I will go to the here I will definitely uh, I mean I will present that this how this game evolving as this game of chance, or there is a game rule, or I have set it out some things. So abstractly, definitely possible, but in a very I'll say that see by abstractly means you want to do it manually, right? Am I
Yeah,
correct?
yeah, you can tell me.
Manual.
Yeah.
So yeah, definitely to test our skills, or if you say very programming or algorithmic point of view, uh, to do these things in a very manual way. So manual way is definitely there will be a definite setup, that is who invented or previously investigated these things. And so if you so there is a rule or there is a setup, so or the equation is there. So you take just random points, and if you keep repeating that random things over and over again, so you will get some patterns. It's not like you just play these things out with 10 times, 20 times, like 20,000 times you have to do this, or 30,000 or 50,000, 1 lakh, billion, million,
No,
trillion,
no, 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 no,
like this.
no. I tell abstract
So,
means it will be step independent.
like, sorry.
It will be step independent. If we getting the 10th step, we will getting the 10th tick, and we will getting the 20,000 step or 30,000 step. It will be step independent.
Step independent, yeah, see, that won't be a step independent. Like, it is not something like you just put a mathematical formula, and if you it will not generate something until or unless you are putting some values in it. But so in a first time you are putting a value, but how, see, how it will, like, I mean, go to the next step until or unless you are putting something new on it. Okay, so definitely you have to uh, put I mean clarify or assign some repetition of the step, that how many times you want to iterate. Okay, so in manually, if you want, if you have patience, you do 10 times, definitely do. If you have patience to do it 100 times, then definitely do. But this is time consuming. So there is computational challenges. Okay. So challenges in it's something like uh, so there so one shouldn't have the patience of doing such thing 100 times or 20,000 times nowadays, even that times as well. So all these things actually generated by iterated these things in a computer system, definitely. But the methodology, the or you can say that what is the algorithms, or is there any mathematics behind it, definitely it comes from the uh, I mean uh, pure mathematics part. Okay, so that is the things I so any more doubts is there? Okay, you jot down your question, so let me approach towards the algorithm part. Okay, so initially this uh, appear like highly complex shapes. So, but when you look closer, you might notice that they follow a relatively simple pattern. All the individual parts of the plants look the same as the entire plant, so just smaller. So the pattern is repeated over and over again at smaller scales. So in mathematics, we call this property self-similarity, and shapes that have it call are fractals. Okay, so now I'll try to I'll talk about a little bit from the probabilistic perspective. Or so if you say that if I talk about something like a probability perspective, it is not like simple the naive definitions of probability things, but uh, this idea will help us to understand probability from a I mean to grasp the idea of probability. Okay, so uncertainty is the profound mystery inherent in our universe, you know. so which eludes the precise understanding. So so there I will introduce a game. So the game will be like game of chance. So a mix of deterministic and indeterministic processes. So a novel concept emerges, that probability. So our main concern is to deal with pattern in chaos. Okay, so in this context, let us engage in the game that uh, unravel the essence of probability and overreaching the objective. So, so here is the setup of the game. Yeah, Indrajit, can you say this thing? I mean, can you see these things? The setup of the game.
Yeah,
Okay. Yes. So everyone, please look into this part. So this is the setup of the game. So you see, so this is the number of appears in the dice. So instead of 6 side of dice, let us assume there is a 4 side of this dice. So where the particle moves following such equation, okay, or such mathematical decorum. So there is a particle which is located at the origin, say in your. So I mean, whatever I'm trying to say, just think about in the Cartesian coordinate. Okay, so the particle is located at the at 0, 0 point. Okay, it's a two-dimensional Euclidean plane. Okay, so it's starting at the 0, 0 point, right? So now consider a die with 4-sided. Okay, and you are seeing that this is 1, 2, 3, 4. Okay, so as the particle moves on the plane according to rules, okay, so initially the particles is at 0, 0. Now imagine that 2 shows up. Fine. So when 2 shows up, then where should this particle moves? Okay, so the particle moves according to this. See, are you getting me? So from the rules described in this table, so the particle move to the following these equations, where this xy is the current our coordinate, and the value of xy at the initial stage, it is 0, 0. So you simply just do is that, so 0.6 times as the position of x. Okay, the value I'm putting 0, 0.19 still remain, and also in the y point, so in the y point this is 0 again, definitely, as I said that you started from 0, 0 point. So x0 and y0, and that's how you get 0.19 comma 0.15. So it will be yes, 0.5. Yes. So this is okay, your x1. That means somewhere in the coordinate system you get the value. So this is your from the initial, then the first, after the first iteration, your value turns into 0.19 and 0.05. Now your x values 0.19 and 0.5. Fine. Now we mark the point 0.19 and 0.5 with the pen. So we throw, this is manually you are doing. Okay, you are doing it manually. So we throw the dice again, and depending on the number, and the particle moves to a different point from our 0.19, 0.5. So if we repeat these steps for say 20,000 times, so of course that requires the help of computers. Okay, so you are doing it 10 times, at least you get you can do it 10 times or 5 times, 5 times. So now if we do this, repeating this, I mean, so that means what? It means what? It means, so yeah, any questions arrive? Do you have R code for creating all this mathematical concept? Yes, definitely. After this, I mean, this setup I have built up in R code, definitely. Okay. So I'll definitely discuss these things. Okay, just hold with patience. Okay. So could you wait for a while? Actually, my this battery is going to down. So just hold for a while. Okay, just hold for a while. As I am. So now next, if I go to the next slide. So this output, you will get such output. Okay. So this is quite look like maple fern patterns. Okay. So these things I have generated in some other way. Okay. In some other environment. But definitely mystery of these things is here. Okay. So we are engaged in the exploration of random phenomena. So in the so so random from this random occurrence lies so in the game where we actively participating in. So the revelation of this interesting aspects becomes apparent when we alter the system of equation in a specific manner. The rule of this entire things will be remain same. Okay, but what I'm saying is that the entire thing, the coordinates, I mean, this how the particle moves, this mathematical pattern, okay, remains same. Okay, so there are a lot of questions coming. Yeah. So can you share the codes? Yeah, definitely. I'll share the code. Is this beginner friendly? And will post it on YouTube. I am completely new to programming and I'm ready to know understanding. Okay. Okay, there is a proper documentations. Okay, so there is a proper documentations in a very layman way. So definitely, I hope Bilikisu will provide the recording in YouTube. So maybe side by side, you just watch that videos and read my blogs and articles. If you find some insightful stuffs are there, so definitely you can look these things out. Oh, okay, so here is a code is there. So let me I mean interpret this code from here. Okay, so you see there is a R function called the P Bernsley. Okay, so okay, so let me zoom these things out. Is it visible? Is the code is visible? I hope it is visible. Let me, yeah. So the P Bernsley, it basically generates and plots the Bernsley fern and the fractal based on the fern algorithm. Okay. So by executing this code, okay, you will see such patterns out there. So this is nothing but fractal patterns you will find. So yeah, let me I can share the image. So I hope my whole screen is sharing. So see this in a very big picture.
Yes.
Okay. First of all, you just see that how this thing is generated. Okay. So there is a, so this is what self-similarity is there? So you see the whole structure of this font image, okay? And you'll find same structure, I mean, similar structure in the branches out there, isn't it? All the branches. Even in the, from these branches, there are some of the leaves, there follows same structure. Okay, so this is the actually Burnsley fern and the Burnsley fern fractal image. So yeah, so let me go back to the code. Okay, so you see the code. So let me clarify the code first. So this if in part is the file name, the prefix for the plot file. Okay, and this n is the number of points to generate for the fractals, and this CLR, okay, this is the color of the fractal points, the title of the plot, and the size of the plot, both like width and this is the size, I mean PSZ argument. So this is the both width and height. So it begins by printing some informations about the start of the function. So including the current date, the value of in CLR, the and the PSZ things, as well as the file name prefix. So it then construct the matrices, the A1 and A2. So which defines the transformation used to generate the Burnsley font fractal. Okay. So these matrices in code are transformation. So maybe some of people, if you are quite aware with such transformation, it is called the affine transformations. You'll find in while explore the linear, if you are following any linear algebra class. So in linear algebra or any matrix algebra things, you will find the affine transform. Basically, it is linear algebra part, the core mathematics things. So so I'm not going to elaborate that things as well here. So yeah, so these matrices encode this transformation which determines, okay, all these matrices. Okay, so here whatever you are getting, so from, so actually I have provided the in row for, in call for, all these things out. Okay, and it is definitely will take row by row, and so this, so so it determines that how each point in the fractal is transformed. So it defines a probability vector as well. You will see. So that P that determines the probabilities of choosing each transformations. Okay. So a very detailed chart or detailed analysis of these things I will provide. So I will provide all these documentations and things which will be in description of this video. So I hope it will be in Abuja user groups YouTube channel. So you'll get that things and all the analysis and all the detailed things, all it every detailed things will be provided. Okay, so no worries those who are not understanding, but try to listen that and try to get the motivations and the insights. Okay, so can you please share links to my articles? Yeah, definitely. So how to catch myself, I will definitely go I will share with you, so you can definitely I share all the links, all the URLs, all my LinkedIn mail things, everything will be there. Okay, so no worry. Okay, so I love your enthusiasm. Okay, so you are quite enthusiastic. So this is yeah, I can't pronounce her name. Okay, no worry. So yeah. So as I'm saying that so P things actually, so these are the probability vectors. Okay. Next, it creates two list of matrices, that is M1 and you see M1, and here it is M2. Okay, to store the transformations which is encoded in N1, A1, A2. Okay. Uh, so it initializes two vectors x and y to store the x and y coordinates of the points in the fractal. So it generates the fractal points. Okay. Um, and points using the loop of iterates of n minus 1. Okay, so you see here I have iterated these things. So it randomly selects one of the 4 transformations based on the probabilities defined in P. Okay, so probability vectors is needed, that what is the chance of occurrence, the chance of occurrence will indicate the system that which transformations I should select, or so it applies a selected transformation to previous point. Okay, so like the xy and the yy things. So using the matrix multiplication, and it stores the result in Z. So it updates x and y vectors with the coordinates of the new points. Okay. So after generating the points, it plots them using the plot function. Right. So with the specified title, color, and plot size. So it turns off the axis and sets the point size to 0 and 1. Okay, so that's how it's going on. Okay, so now it is I have shared this okay, this is a static one. Okay, so let me give you the flavor of visualizations, the animation. Okay, so I hope you can see the slider attached out there. Okay, a local hosting is happening. Someone please say that you are able to visualize. It is displaying in your screen. Is it displaying in your screen? Yeah, is this whole screen is displaying a slider attached here?
Yeah.
Okay. So you see, as per
Yes.
my condition, there is a fixed point. Okay.
Okay.
So you just consider this as a 0 point or any stable point out there. Neutral point. Okay. So if I just start play, you see how it's following the condition. So more it moves, more you will see that how this growth of this fern is going on. So is my entire screen is visible to you, or should I move this thing?
Yes. Yes. Yes.
Okay.
Yes.
Okay. So see these visualizations until it reaching this 99. So let me have some water. So this is it. So now your question could be that can I do this by so yeah, these things also have some codes, okay, made by Plotly and the animation slider, Plotly animation slider. So definitely I'll try to provide these things, but actually I am facing some problem to attach this entire frame, I mean the animation frame in my blogs because of some technical issues or any browsers or the server issues. So I'll try to develop that things, but still the insights or the main understanding is necessary. So now you can question me that can we increase this 99 to 100, 150 to 100? Yeah, they definitely possible, because definitely possible. But why I am not doing these things? Because it is not supporting my system. My system will hang. So the same thing I just previously said, and to recall that things, by recalling the things, that is, you need the support of better support of computing system, like you need like if you are searching for I mean high performance of RAM cores, everything, so you won't get do these things in a very your personal computer or laptop. So you need laboratories or any somewhere where, I mean, the a better configurations of your system, which can help you to perform such iterations, such more computational things. So yeah, that is the thing. So let me go back to my slide again. Okay, so so the artistry of growth, that is the next topic. So so you just picture yourself standing in lush dense forest surrounded by towering canopy trees. Okay, so reaching towards the sky, as you gaze upward, you're uh, mesmerized by the intricate patterns and branching structures. So the canopy of a forest is like a vast green umbrella, providing its shelter and habitat for countless organisms below. So similar, the fractal nature of canopy basically mimics the self-similar patterns found in the fractals. So where each branch and leaf uh, is a miniature reflection of the whole. Okay, so just as a single canopy, but tree can be seen in a uh, an entire forest ecosystem and its microhabitants inhabitants. So a fractal canopy exhibits a similar principle in a, I'm sorry. So in a visual scale. So zoom in on any part of the canopy, you will find the same repeating patterns branching out infinitely. Okay. So like a natural work of art crafted by the laws of mathematics and growth. So I have tried doodling these things out in my digital board. So 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 you can try this doodling things out. So if you are doodling uh, with a pencil of a piece of paper, like drawing simple lines. So now imagine you decided to get a bit fancier and split that line into two smaller lines and at the end. So next you decide to do the same thing to the each of those smaller lines, splitting them into even smaller lines. So you keep doing this over and over again, each time splitting the lines into smaller and smaller pieces. Okay, so that's essentially how a fractal canopy forms. So it starts with a simple line, okay, and then it gets split and branch into smaller lines sequentially. Okay, so at the end of each line, new lines are drawn at specific angles. That's why I written in a theta. There's a angle definitely. So yeah, so there are a bunch of things you can tweak and to change how the fractal canopy looks. So you can play around with the number of branches, deciding how many lines to split each uh, existing into line. So you can also adjust the angle between the branches, determining how they spread out from each other. And don't forget about the original width of the line and how that changes as the branches get smaller. So it's like having whole toolbox of options to create different kinds of fractal canopies. Okay, so 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 now our investigation. So we are investigating here the implementations and the application of iterative drawing algorithms, particularly focusing on recursive tree generation. So the primary object is to explore the, uh, reason behind the development of code segments, and we aimed at creating intricate trees like structures through iterative process. So before going to dive into this, so let me open my R script, okay, and let's do some warm up. So we'll first start with some very basic things. So this is the function I have created. I named this as the empty canvas, you see. So this function actually creates an empty plot that specified the XY limits. Okay. So, and the BG means the background color. And so it demonstrates uh, uh, how to use the empty canvas function by creating an empty plot with x limit 0 to 1, okay, and y limit 0 to 1 as well, with a gray background, okay, or here the things, yeah. So let me run these things out here once, so I can show you that how. So this is the empty canvas, okay, this is your empty canvas. So empty canvas has generated, right? Next thing is how to draw a single line, okay. So these are some parameters, okay. So first thing is line, is the col the COL, that is the color with white, the color of the line, and the thickness of my line, okay. So this is the draw lines actually. So this function draws a single line given its coordinate. Okay, we have plotted our canvas, our system. You can compare with as your XY coordinates. Okay, so using the so it takes parameters, as I said, these two. So the segment function, okay. So the segment function uh, uh, takes the parameter of color and the thickness only. And x0 is my first line, y0 is my second line, x1 is a line after second line, then the third line, and y1 is the fourth line. So now I have also prepared a draw object function. So the draw object function represent as matrices where each row corresponds to line, and it applies the draw line function to each row of the input matrix. Okay, so and definitely all these things out here storing into a vector called mat, the matrix, all these things. So let me run these things, I mean execute these things out. Okay, yeah. Now I will draw the lines separately. So first thing is empty canvas. Okay, so this is my empty canvas argument. Okay, so I have take the limit minus, I mean, so you have to set the canvas, so xy limits. So empty canvas first. So you see, this is the limit. I mean, this is your empty canvas within the range. Okay. Now I'll draw line 1. I'm sorry. Okay. So where is the problem? Okay. Good. Yeah. You see, this is the line. Now I'm taking another way. I mean, draw our line 2, and I am providing a color here. So this is a draw line. I'm sorry. So let me run these things in a very complete way. Yeah. So you have to execute whole things out. So if you just only, execute the draw line, okay, the system won't be recognized that from where you have to draw this line. So first you have to execute this empty canvas and then this thing, the whole things. Because if you, I mean, see, it is not something that anywhere you are just drawing these things out. I mean, so the system will not be able to recognize that in what range, or I mean, it won't be possible to take the limits or any certain range or certain points to draw the lines. Okay, that is the thing. So you have to be you have to clarify your system, your R system to that in a empty canvas with the limit this, you have to draw this, you are going to draw these things up. Okay, so similarly you can play these things out here. So this is the warm-up, and next we'll go to line draw part 2. So you see, here I have written so much of functions out there. Okay, so step by step I'm just elaborating this thing. So a function new line here I have added. So the new line function takes our 4 arguments. That is the coordinates, the line, that is the coordinates of existing line, angle, So the angle in degrees to add to existing line and reduce. So a scaling factor for the length of new line, and default is 1. That means uh, I mean uh, you could mention the LWD here, so that is the thickness of your line and things. So that is why I'm saying the 4 arguments, but I haven't take this LWD. So by default it will be, because I have already executed things out there. Okay. So now so it calculates the changes. Okay, here you see the next thing is dx and dy and this L. Okay, so it calculates the change in x and y direction, that is dx and dy, of the existing line as well as its length, right, L. So it calculates the angle between the existing line and the origin, that is the theta, and converts it to the radian. Okay, so it determines the coefficient of directions based on the sign of the angle and the change of y directions. Okay, and see there will be a new x and y coordinates, that is our x2 and y2, for the endpoint of the new line based on the angle of the scaling the factor, and it written the coordinates of new line as a vector. Okay, so as per example we can try these things out. So how? So I have written I am example. So this new line, okay, so it demonstrate that here so this new line functions by demonstrate that by creating a series of lines, this A to E, based on successive additions to an initial line. Okay, so each new line is created by adding an angle to the previous line and optionally reducing its length. Now drawing the lines. So it utilizes, okay, so I'll run these things, but before executing these things, I am just elaborating, and we'll see the beauty of these things, what it creates. So it is it utilizes the previous defined function empty canvas and draw line. Okay, so draw each line on a empty canvas with a specified limits and colors. Okay, so let me execute. And you see this. So when you are at the very beginning of your drawing class, okay, maybe in at the age 5 or 6, you started with such things, isn't it? So now these things you are doing writing the codes. Okay, again one more question, can I get the YouTube name, and can I get the YouTube name and your LinkedIn, sir? Yeah, YouTube is like the Abuja user group. You'll find the recording. So my name is, I'm typing, this is Abhirup Moitra, and you just search my name in Google too. So I hope you'll find. So yeah, this is my name. Okay. And yeah, yes, I keep getting kicked out from this meeting. Okay, don't do what? Okay, I think it's my network connection, so I'm rest of. Okay, okay, no issues. You can go through my recording. Also feel free to connect. Okay, by email and LinkedIn as well. Also by following my articles, and I'll apart my
I
article.
think I think you're similar to Young in this website.
What?
I think your Gmail was Young.
My Gmail is wrong. Okay, I'll see. I'll see. Oh, if I get any error there, I will definitely work out. Okay. Okay, fine. So let's get back to our coding part. So you see, overall, this functions on whole things allows for the creation of new line based on specified angles relative to existing lines, offering the flexibility in constructing uh, uh, complex geometric patterns or shapes, you can say. So here is our next thing. So here I hope here I no need to elaborate. Okay. So here is so you see the draw line, same thing out there. Okay. Here also draw object. So this draw object. So this draw object function is a wrapper around the draw line to draw entire objects. Okay. So which represented as matrices where each row corresponds to a line. So it applies the draw line functions to each row of the input matrix using apply. And new line here, sorry. So new line, the same as oh my God. Yeah. So new line, I hope I know need to demonstrate the same concept and same arguments there. Not same, there is little difference. Okay, so the thing is, so this functions basically adds a new line, okay, to an existing one based on a specified angle. Okay, optional reduction of factor. Okay, that is reduce things is there. So I am using this to calculate the new endpoint of the line based on the angle and reduction the factor relative to existing line. Okay, so also I have introduced here a function called iterate. So this function will help you to iterate over each line in an object that is I mean the matrix of line, and applies a specified function that is ifun here I have provided, so to generate new lines. So also it stores the new lines in a list of, combines them into a new object of matrix. Also the tree functions, which is a recursive tree. So you see this is a main function to generate the tree structure recursively. So it takes parameters such as the initial line and branching, the angle, reduction, the factor, and randomness. Okay. So we also calculate the angles for the left and right branches, adding some randomness to each angle, and new line segment, the line 1 and line 2, okay, based on the angles and reduction factor using the new line function. Okay, so it stores the new line segments in a matrix and returns it. Okay, so let me execute the whole things. Yeah, maybe some sort of things will not be able to grasp at a time, so don't worry about that. I'll share proper materials if you're really enthusiastic and interested about this. So next, so overall this functions work together to create visualize a recursive tree, the setup of your recursive tree, and structure it each iteration. Okay, now all these things are done. Okay, so now here is the first iteration of our this whole thing. So this is the first iteration I'll do. So you see the very beginning and the first iteration what you get. So this is your trunk and these are the two branches out there. Okay, and here also, so this is the first iteration, then we'll do the second one. Let's see what happened. Oh great, from this two branch there are more branches out there. Okay, so if we keep repeating these things over and over again, let's see what happened. See, at the very sixth iteration you are getting like this. Now coming back to our PPTs, see, so at the very beginning of iteration we are getting such things. Now when you will reach after iteration 10, you'll get such things. So let me zoom these things out, and this is like 12 or 15 iterations by just mentioning the color. So what is the changes you need to do is that, so in a draw object just provide the color I+1. so more it will iterate, more the color will changes, and automatically you will see that how more it will grow, more the color will changes. Okay, and you'll get a beautiful pattern out there. Okay, okay, fine. So there is another way. Okay,
Sir, this coding where this is application, where use which purpose and where
see,
this application most important.
yes, yes. So this is the very beginning, okay, to work with. So in a very robust applications like a canopy trees or canopy fractals, actually this canopy growth is quite meaningful when studying of cancer cells, the growth of cancer cell. Okay, so in medical researchers, I mean not medical researcher, in medical sciences, the application those who are developing from I mean contributing from the image generating and things as well. So the growth of your cancer cells or any such what should I say, So the veins structure, to study the vein structure of your body, to get the image of your that things. Okay, I mean, it is not always, see, when you go somewhere for I mean diagnosis purpose, it is not something like doctor always like cutting your I mean chest, or cutting your brains, okay, I mean scalp, and then starting these things out. It's all about their I mean writing the prescriptions, or I mean uh, to go for USG, or go for the MRI. Okay, I hope you are aware with the MRI. What do I mean by MRI? So what's happening?
Yes, sir.
Yes.
Yes, sir. Yes, sir.
Yeah,
Thank you.
don't say me, sir. Okay, don't say me, sir. This is embarrassing. Okay, so
Sir, but are you which semester now? You completed MSc or PhD?
no, no, I'm pursuing my MSc. Okay.
Oh, but you know Rentu in IIT Bhubaneswar, mathematics.
Sorry.
Rentu, my friend in West Bengal.
No, I'm not aware with this name, this guy. Fine. So
Okay.
let's come to our discussions. Okay.
Okay.
So
Okay, okay, sir. Okay, okay. Sorry.
just yeah, mute yourself. Yeah. Thank you. So yeah. So when you are going for the, yeah, someone is there, just I will say just mute yourself. You just mute yourself. Actually, it's disturbing. By, yeah. Thank you. Thank you. So what I am saying is that, yeah, if you have any particular question,
Okay. Sorry. Sorry. Let me
no,
come in
it's
here.
all
Please,
right.
if you have questions, hello, so that we
Hi.
don't do too much of editing. Please, if you have questions, just let's signify. Then we have in kind of orderly way of
Okay. Okay.
organizing this.
Yes.
So
That's
please, just let's know who is asking questions. If you want to pass
whoever
comments,
is
then
asking
let's know.
question, just put it in chat box. Actually, the
Okay.
problem has happened that in between my talks or whatever I'm sharing, I mean distract with the main topic. Okay, so yeah, that is a very specific question that what I am saying. So when you are doing the MRI things, okay, so MRI, so when the image, so it is not like the just capturing, and like it is not something like this is your digital camera or phone camera, like you're capturing things. But yeah, definitely capturing things and to visualize these things, pixel and things, the algorithms, the things what's going on, the mathematical or the algorithmic point of view, there's also uh, these things works. But specifically to growth of uh, cells or any vein structures, or studying any like the CT scan you do, okay, to what is the problem happened in your brain or any body parts. So to study that, those sort of things, and to develop such machines or image generating stuffs, we I mean go for this methods of fractals. Okay, so yeah, one more questions is there. Thank you. So I hope you're clear with your doubt that where we need to work. So actually there are so many applications, so many I mean uh, places
Uses.
out, but especially I work I mean uh, basically I personally interested to work with the mathematical part, as I am saying that iterated function system, I'm studying these things out. also I play these things out after this talks, after this webinar. Don't someone I mean get the proposal, sir, just teach me these sort of things. I don't teach these things actually. I just implement my thinking and creative things in using art. Okay, nothing very special and nothing very uh, so you can also try these things out. Okay, so but there are a lot of resources. I'll share the footnotes, whatever I have taken help. So Wikipedia, I'll say, is the best resources. More you'll search there, you'll get so much of information. And coding environment, whether you can do in R, Python, anywhere. Okay, so it doesn't matter. Okay, uh, even what it is, MATLAB. So MATLAB, Julia, you can try these things out there. So yeah. uh, yeah, I have a WhatsApp community, so I'll share these things out. Okay, so I'll add you. Okay, definitely. Thank you. So here is a complete fractal tree out there. So I have generated these things. So it is nothing complicated. So you can see you can take one patterns out there. Okay, this is nothing but I'm segregating all these patterns. I have just nothing, just I have collaborate and join these things out. I collate all these things out and just generated this image out there. Okay. So, okay, let me go to the slides. Let me go as per my slides. So here is the artistry, uh, as I said here. Okay. Also, this things is very much interesting. The codes, everything, the every detailing is in my website, so I'll share that. I'm not going to describe all those things, otherwise this session will take another 1 hour. Okay, so I don't make these things very lengthier. So this how this GIF or this beautiful structures out there get generated. So I'll share these things out definitely. uh, so next is the our Pythagoras tree. Okay, so this is I'm sorry, yeah. So Pythagoras tree is okay, let me show you the code. Okay, and then we'll go to the generating part, that how I have generated. So this code are quite lengthy. The length of this there are so many things I need to mention, otherwise the session will too long. I thought that I will be able to cover all these things, but it seems to like I have to avoid some sort of things. Avoid means just not to discuss here. Maybe in some other session I'll discuss these things out, or the whole tutorial is out there, so no worry. So yeah, let's go to the Pythagoras tree there. So this recursive function, okay, this is pi tree. Okay, so this is a recursive function. Okay, so this function plots a single branch of Pythagoras tree. Okay, so it takes parameters ax, ay, bx, and by, and d representing the starting and ending coordinates of a branch and its depth. So it calculates the coordinate of the vertices based on the Pythagoras theorem, definitely, and plots the branch using segments. Okay. So it recursively calls itself with update coordinates to plot the sub branches. So maybe you see, maybe some of the fractals images, or I mean some of the fractal structure may not be always directly used. Maybe it helps to generate, or it helps to build some another thing. So if you see the previous slide out there, so here when you just I mean slow motions, you just wait, watch this, the growth of this. So you see everything out there from to this, the I mean how the thing is collating, and this then it's blooming out there. So here you will see some patterns of this Pythagoras tree. So so not necessarily that all those fractal trees or the fractal algorithms will be directly applicable. I mean, directly used in in what should I say? In directly in applications. To develop some algorithms, we need such kind of things. Or simply you just trying to study these patterns out there. So yeah, I'm also a practitioner of this field. I'm trying to study these things out, mostly doing using R. So, and here it is the this function. I'm sorry, this P Pythagoras T. Okay. So, oh, also one thing I just missed, that this recursively the calls this coordinates to plot the sub branches. We do it recursively as well. So now I can't explain here what is called the recursive things. I mean the recursive function things. This is completely the part of computer systems and data structures things. When you will study the data structures in your course, or if you studied before going to implement these things, just go through that things as well. Even it is not like that I know all those things. Even I also revise these things. The revision is important, and to understand the deep meaning of doing implementing the algorithms. Okay. So so these functions, P Pythagoras T, so it is the entire Pythagoras tree functions. Okay, so it takes parameter x1 y1 x2 y2. Okay, and the TTL representing the starting coordinates, order or depth of the tree, and file name or saving the plot with title. Okay, and it initializes the variables for the plot sizes and name, file name. So it plots an empty canvas first and calls the the pi tree, the this functions to plot the tree branches recursively. Okay, and we save these things up. Okay, so I have do these things with the different orders 10, 12, 15, 17 to generate the Pythagoras tree with varying the complexities. So each tree is plotted with a specified starting positions in depth, and you can see these things out from here. Okay, so this is the order 10 and this is the 12, 15th and 17th. So more you will iterate, more you will get better shape, better I should say the better image it will generate. So this all the codes I have shared till now, about this Pythagoras trees flexible way to generate the plot Pythagoras tree and different orders, allowing the customizations of starting positions, depth, all those things. You can also, there is no hard and fast rule that this is the only way to work or only algorithms. You can build and play with your algorithms. Okay. And here we are some geometric fractal images. Mainly what fractal image we mainly study is first, that is the Sierpinski's triangle. So this triangle named after the Polish mathematician. So you can see this name. So Sierpinski's triangle is one of the most iconic geometric fractals. So this fractal is formed through the recursive process, definitely, of subdividing of triangles into smaller triangles. Okay. And this, so you can see this, how these things dividing things up. So you just, so definitely this is experimented in the equilateral triangle. So with a smaller equilateral triangle uh, comprised with equilateral triangle with smaller equilateral triangles recursively and removed from its remaining area. Okay, so this triangle here out there, so from so one so what happens, what is the algorithm, what is the methodology is that we'll cut these things out with equal. Okay, so that's how we'll do for every step recursively. Okay, so this recursive removal process creates a fascinating visuals effect. So wherein the final shape consists of the three identical copies of itself. Okay, so now I'm going to the direct in the coding part, that how these things work. So this Sierpinski this. So this is the things, the constructions of this. So the construction of this triangle follows a systematic progression. Okay. So I'm not going to explain all the codes because it will be too long. Okay. So next thing is this Sierpinski's carpet. Okay. So yeah, first at all, let me. So I hope is this this is visible, that if you do keep go on this process, how it look like. Okay. Now a question can arise that why we are doing this triangle. I'm going to that question, that thing. So this carpet, okay, this is the construction of this carpet. So it follows a straightforward iterative process. Okay, so this begin with a square divided into 9 equal smaller squares arranged with 3x3 grid, and similarly, as per this triangle, we are doing these things into the square triangle. Okay, so this is the main constructions, or main you can say the setup of this triangle. Okay, also, now what is interesting part is that the coach snowflake. Okay, so this coach snowflake is a very important part. So actually, starting this coach snowflake, we are doing these things out. Following from the from the Sierpinski's triangle process, we are following how that will be explained in later on in my when I'll share the materials. Okay, so you'll see how I just answered that things, that how it is developed. And also I'm writing so many articles, working on articles to prepare a proper documentation of this. So Koch snowflakes is on a this so the its core is that So it emerges from a very simple iterative process. So start with a equilateral triangle, then replace the middle third of each line segment with two segments of equal length. Okay. So forming a smaller equilateral triangle, repeat this process infinitely for each remaining line segments. Okay. So this is the idea. So see, the geometric fractals not only captivating the imagination, but also have some practical applications in various fields, like the computer graphics, image compressions, and even the study of natural phenomena like coastlines and clouds. So you see, specifically this Koch snowflakes, and there are so many um, fractals images or fractal geometry stuff. The algorithms helps to study the coastlines and clouds formations. Okay, so to predict the weather. Okay, the predict the, I mean, any such tornado comings. And coastline means it helps cartographers. I mean, the analysis will do someone, but cartographers, the geologists, they actually helpful by these algorithms or by this analysis. Okay, so definitely a computer scientist or any mathematicians or who is interested in the computational part of mathematics will be interested to do so. So their works will be help another to do such things. So in the realm of science, the study of these geometric fractals serves as a reminder of the inherent order of complexities that permeates the natural worlds. So from the intricate patterns of snowflakes to the sprawling the landscape of coastlines, fractals offer a window into the hidden symmetries of patterns that shape our reality. Okay. So we embark on a journey of discovery that unveils the wondrous beauty of nature's infinite complexity. So here are some footnotes. So you can search these things out. I will in every of my articles you will find very my this footnotes. Some of them. So this is a fractal garden. Okay, footnotes, and this mathematical playground where you will see lots of I mean explorations that how they design these things, studying these things. Okay, so from the mathematical perspective. Also, you can see my articles. It's unraveling nature's code. Okay, the fractal flame algorithms, analyzing the fractal complexities, which is a comprehensive analysis of my iterative function system. Also, there are some of two Wikipedia links there, and feel free to reach out from my website, the Abhirup Moitra maths@netlify.app, and this is my email ID. Okay, you can take a screenshot. This is my LinkedIn ID. Okay, and here is my community called the Era of Chaos. So where I study, updates the study about pure mathematics as well as this chaos and dynamical system fractal things uh, there. So yeah, thank you for listening. Actually, I am honored that the people who have listened from the beginning to end. So thank you for your patience and thank you cooperating. So I'm ending these things out here and hand overing this platform to Bilikis once again. Yes. So any questions are there? So you can stop recording. Okay. So yeah, now I'll try my best. Yes. So this fellow is uh, keep repeating to share my email ID. So yes. dear. Okay, fine.
Okay, you can hear me?
Yes, yes, yes.
Okay.
Yeah, Misbahul Islam is
Okay, I
saying.
want to use this opportunity to really thank you for. Yeah, I hope everybody. I've really enjoyed all this artistry, and I hope I will have time to look at the maths behind it. So if I have any question,
No, yeah,
I know,
there
I
is.
know, I know how to get you. I know how to get you. So thank you everybody for joining us today. It's been a wonderful time. I believe
Yeah,
when we get our hands on the R code, we'll be able to make some tweaking around and kind of manipulate it for ourselves. So thank you, Abby, so much. I'm really grateful for your support. We really appreciate you.
thank
And
you.
we look forward to really having more fun together. So thank you so much.
Thank you, thank you.
And thank you everybody for joining us today. So we look forward to having fun next time. So it's bye-bye from me
Yes.
and from everybody here in Abuja, our user group.
Okay.
Thank you so much.
Biliki, so one thing I'll say that maybe tomorrow or day after tomorrow share all the details of my documentation,
Okay.
codes,
Okay.
my
Awesome.
contacts. Okay, so you just
Okay.
put it in the descriptions.
Yeah,
Okay.
I think that will be useful to add to the YouTube channel description as well.
Okay. Yes.
So we'll add that. So whoever wants to get more information about
Yeah, whatever
what
I
you've
have
taken us
shared,
through
that
the
is
time.
the part of my documentations. Okay, so I'll share all the documentation.
Okay.
So you can
Okay.
read
Okay.
everything.
Okay. Awesome. Awesome. Thank you so much. We're really honored to have somebody as passionate as you, and we look forward to having more fun with you next time. So thank you, everybody. Thank you for your support, and we look forward to meeting you next time. So
Okay.
Thank you.
stay
Bye.
safe
Yeah,
and
sure.
keep learning R. Bye-bye.
Yes. Okay, bye.
Bye, dear. Bye-bye. Bye-bye, everybody.
Actually, I'm not able to how to get out of this pause share. Okay. Actually, I don't know how to pause, stop sharing. Okay, I will leave.